have, since they were invented, so to speak, in, I guess, the late 90s, they come together with models. What is the allowed variability, multidimensional models? What is the allowed variability within such a product line? And what this particular paper does is to try to combine these ideas with non-functional requirements. And again, it takes category theory that we have already learned about, so we don't need the introduction again in this talk. Uses category theory to evaluate possible solutions for this combination. The work was done jointly between University of Malaga in Spain and the KTH Royal Institute of Technology in Sweden, Stockholm. It will be presented by Daniel Jesus Munoz, joint work with Lilian Burov, Monica Pinto, and Lydia Fuentes. Please share your screen and go.
Yes. Can you hear me well? Can you hear me?
Yeah,
yes.
We can hear you.
Okay, good. See. Oh. I want to access the menu, but the screen is so small. It's closing. See if I can resize the screen. I just cannot access the button to press present. Is there any keyboard combination to
Percentage mods? F5?
Yeah. F5? Okay, I will try. Yeah, perfect. Thank you. You saved my day. Okay, so I will move this here. Each part of the title is important. We are covering many stuff, but thanks to the previous speakers, and by the way, your talks were really interesting. I don't need to introduce the part of the category theory and not much of the requirements as well. As they mentioned, it was a collaboration from KTH and University of Malaga. It was till the last minute decided because with the COVID, it was difficult as I moved there for an internship, but finally we could do it. So I thank Professor Dillian very much for hosting me and doing every paperwork, because with the current situation was really difficult moving abroad. Let's start with a bit of software product line explanation. This is a really crash course. We have a system, usually a highly configurable system that we want to analyze. Then we have a model that represents that system. And that model is the input to automated reasoners. The basic reasoning that the automated reasoner will do is to generate one solution or to check the satisfiability of that model. And then it will generate, as I said, for example, one product. But another inputs are the user requirements or the developer requirements that constrain the model externally, and also the objective. This is more related to the optimization. If you want the most optimal solutions or near optimal solutions, or also if you want to generate all the possible solutions, is also the default behavior of some reasoners, generate all the possible or valid solutions. Then comes the situation. It comes a client, and this is an imaginary situation, by the way, but it comes a client and asks us, could you analyze our highly configurable system? And obviously, I'm the SPL engineer. Yes, sure. It starts describing the system, and it starts, okay, it has some components and alternatives. Okay, maybe with a subsolving, I can do it. But it has also arithmetical requirements. Okay, maybe I need to move out to other larger models like SMT or constraint programming models. Okay, it has quality measurements. Okay, maybe a hybrid model, because the previous model doesn't support straight ahead quality attributes. And then it has system requirements. Okay, I have cross-tree constraints. And then we have cross-quality requirements. Okay, this is too much. There isn't a single model right now that can do all that, and that is connected to an automated reasoner compatible with that. So I did what everyone will do in Sweden when it needs to solve something. I went to the Laplands and asked Santa Claus, what can I do to solve this? And he told me, no way, there is no solution right now. So I needed to think and read the literature, what can I do? And this actually happened in the scenario of the edge computing. Why? Because edge computing deals with like locally distributed computation, and you have many sensors, many variables. It's not like a monolithic coherent system. You have really numerical stuff, cross requirements. It's really complex. So we needed a solution to solve this. Then, which is the current trend in modeling in my community? The first one is, and the most common, is extending, because we don't have standards yet. We have like consider standards by some parts and others by another part of the community. But the main approach is extending. I have this model we've been using like this way, and we add new functionality. Sometimes they do it to the model, but the reasoner doesn't support it yet. But I will not enter into the reasoning yet. But this is what we usually do. We extend models. Second option is we create new pseudo standards. We take something from this one, something from this, another pseudo standard, let's say pseudo standards A and B, and I create something new that is smaller but more specific for what I'm trying to solve, and maybe it works for that. But you are adding a new pseudo standard. Sorry, I need to press. Also, it's the hybrid model of transformation. I transform one model in A into B, and now it works. Or I use two models and I create something in the middle that interconnect those two models, and then both reasoning, independent reasonings works together. I did this option as well. And then it wasn't enough, it gets too complicated. So we tried the unification. And I mean with unification, not creating new standards to unify everything, but something that will use what already exists in a simple way. So it's an auto-extension. Let's talk about the extensions that we needed to cover. Here we have the variability and quality attributes modeling. Regularly in SPLs models, follow this tree graph-like hierarchical structure. There are some exceptions like the propositional formulas, but I will not enter into that. Some extensions here that you can check are, for example, first of all, the quality model, the quality attribute model. Regularly, you don't find quality attributes integrated on variability models. And they are, and less of all the requirements, like performance there or energy consumption. The way we are currently modeling them is like small consensus, is like a list or a set of quality attributes linked with products. So this is, this product takes this time to run. So you are connecting the complete products with quality attributes. Other extensions are, for example, numerical features that you see there on the left and right side. In this case, integers. Why? Traditionally, variability models are Boolean, and you have Boolean logic like cardinality or an XOR. But when you add numericals, you need many more. You need arithmetic. Because you need to consider the constraints, and you have mixed constraints like logic inequalities with with mathematical operations. You have also labels, and in this case, clonables. You have to clone their feature y1 and feature y2. When you have a label, you can create few instances of that label. So here are many extensions, but to have it clear, this doesn't compile. What I mean that doesn't compile, there isn't a reasoner yet that can do all these things and can understand all these semantics at once. So that's why we need something that unify, because we have one model that takes numericals, another model that takes the Boolean and regular stuff, another for quality attributes. We need something that unifies all these things that are going on and are developing independently. And yeah, we have it here. As they explained it before, but we have category theory to rescue us. If I need to summarize it in a sentence, is the unifier of apparently dissimilar models while abstracting individual specifics. What I mean, it takes what are common between different models. For example, the tree graph-like hierarchical structure that I explained before, and also abstracting from if it is Boolean, if it is arithmetic, and so on. It tries to cover everything and join everything by their common aspects. I won't enter too much into the category explanation because my colleague before explained a little bit how it is. But then we have categories and are formed by objects and arrows. And they represent related spaces. And the objects are extractor classes, and the arrows are the functions between those classes that preserve those extractors. They need to comply with identity and associative composition. So that means self relationships and composition of relationships. In my case, we have the functions that map categories. We have something extra. This comes from the applied category theory, so it's a more straight for usage categorical explanation. We have paths, that is a sequence of relationships and a sequence of arrows. We have the generalized elements. In this case, is the select unit of it's an arrow, a select unit, the select unit object from to another object. Regularly data types or can be also a structure objects. And the instances is the set value function for elements, is giving a true value and a specific value, numerical value, Boolean value to an element, the elements. Something to mention is the flexibility of category theory. A single object can be a category. And a category can be formed and divided into subcategories. So sometimes what you define as a category, it can be an object because it's a single object category in a upper category. Okay, we will use this later on. Then what I propose, simple. Variability models or quality models in general, relational models are categories. The relationships, constraints, requirements are arrows, are the relationship arrows. Features definitions are generalized elements. So that's like the variables in a programming code, and their values, their current value, are the instances. So giving the value to those elements. This is the category of the numerical variability model, that the same example as before, but now is categorized. As you can see, we have the two clones, the ones that were feature Y and feature Y1 and feature Y2, previous example. We have these are T3 and T3 star. The hierarchical relationships are the arrows, parents and child. I omit certain things here to don't complicate the graph so much, like the cardinality, but they are just elements or arrows of the different objects or relationship between categories, because they are also here self relationships. Then we have the objects of the data types. I summarize them with a cross product, but obviously you will have one for the characters, another for the integers, and then you have the string, the name value of different elements forming a category. And then those data types are also relationships. We are just saying that this element, generalized element of this DOM, has this domain, it's a numerical feature, and then you instance it with a value. And also you have the cross-object constraints. I put them down right there. Just don't fill the graph with many crossed relationships and arrows. But yeah, you can. They are also relationships between objects. Then with the quality attribute model, this is more simple. You have a single entity with following its elements follow the domain name value domain. So for example, performance, numerical, an integer value in seconds. And also the self constraints like the non-functional requirements, performance less than 10 seconds. These are arrows with that specific constraint. Then we have the interconnection, because that wasn't also clear on the software problem like yet, and I hope this will help to that. It's how to formalize the connection between the models, the variability models, and the quality attribute model. And then I need to say that in category theory, you need to define, and you can define intermediate objects and intermediate structures. And also the result that you will get from the automated reasoner, you need to define it as a resulting category, because you are just moving and connecting data from one place to another, even if you modify it in the process. And here what we have are the solution spaces. So we have from the left side all the products that we can create, valid products, and on the right we have the measures of those products. What's happening usually in an SPL, you don't have all the products measured. So we have there the subset, the space subset of the products here called complete solutions to be more formal, that are measured. And you have a bijective relationship, in this case as a function, between the measurements and those specific products. Like for example, this piece of code takes this time to be run. Now, we apply this framework to a hybrid tool that we have, a hybrid modeling tool that we have. It's called the HADAS. HADAS is made for edge computing. As I explained before, is our problem to solve. And as you can see there, we have two main subtrees: is hardware and software on the left side here and here. And then here you have four subtrees: context, programming languages, operating system, and operations. What we're trying here is to represent every type of system in an edge computing environment. And then here we have the quality attributes model. So as I explained before, we have the performance in seconds, and they are connected just with the leaps of the model. Why with the leaps? Because having a hierarchical relationship bottom to top, we already know the trace of the product. So if we know that we have libraries, we also have a context and a software, and we finish on the root. Then applying the framework, we get what we have on the right. As explained before, subtrees are objects. So we have here the hardware object, the software object, and then as subtrees connect context, programming language, operating system, and operations. We have the cardinalities also as arrows. Then something that I explained before about the flexibility, instead of having two related categories like the quality attributes category and the variability, we integrate it as an object, because the quality, as I showed here, the quality attribute model is a single object besides the data types, a single object category. And then we connected them the same way, just by the leaps. So we have some intermediate, it's called solutions, intermediate object that connects leaps they are considered leaps from the other objects, from the variability, and with the respective metrics. We applied that because that was an example of how the framework works with a real model with data. So this is an edge computing model. It's not the biggest one, but it works to test and evaluate our solution. As you can see, it's really simple. We have some devices like Bluetooth chipsets and so on. We have different computers that are running them with different CPUs, like the Snapdragon, a Raspberry Pi, etc. Then we'll have different operating systems, and we have different operations like compression or sending, receiving data, and some numerical nodes or features like the data size or the packages when we are compressing that we are sending, how large or short are those patches. And what we deployed and programmed this here on the on what you can see on the right is just a little snapshot. It's done on the COL IDE. It's the state-of-the-art canonical functional programming environment. It's used for category theory, and it already allows to model all what I explained before, and also it integrates different solvers. So it allows us to process the framework and also test it and use it for evaluation. So there is a difference on the reasoning process. Before, what we had was, as we can see here, we have the variability model. In our case, was a constraint programming model with a database. All this quality model was a hybrid system, and it was on a database. But then when we move to COL IDE, what we have is moving from that to a automated theorem prover with Bendix for logic and the equations, and hashing, balances, and chasing for the data types and cross-object arrows. So the reasoning process is different, so we expect different performance. A simple run that is generating all the products that are measured gave us 162 products. And each of them has two measures. It has the performance in seconds, and it has the energy rate in watts, giving 324 measurements, and all that in 0.1 seconds. That's much lower than we were getting on this hybrid system, because then you have some intermediate interconnection that really doesn't scale much. Then we have the subcategories. It was decrease the system, decrease the instances to have a shorter model, and also it takes 0.1 seconds. We triple cross the model as well to have a larger in size model, and it took 0.2 seconds. So it's not much more for that increase. Hence, we concluded that this, while we are not measuring the scalability of the IDE itself, but that our model scales linearly on that IDE, and the minimum runtime for it seems to be 0.1 seconds. We tested it on different computers and environments, and the minimum accounting for was 0.1 seconds. Probably because it's a Java application, so it runs interpreted. Then we perform a regular analysis, like trying to maximize, to minimize energy consumption and maximize performance, decreasing the number of seconds that takes to run every possibility. And we've noticed that compressing data increases the energy rate, but also that powerful CPUs barely affects energy consumption, besides if we are compressing. Probably is related with the first caveat. And also that communication peripherals didn't affect much to the communications, but there is a slight difference where the Wi-Fi is a bit more efficient for large data sizes and large batches, and Bluetooth it consumes less and is faster for small data sizes and batches. Then concluding, the extended variability models with quality requirements can be represented as categorical objects and arrows. Even if it seems a simple definition, it has some workaround when you are transforming one thing to another, but it can be done. And then when you learn it straight ahead, and also that our category theory framework is viable approach, and that is scalable on this concrete COL IDE. There are many IDEs that you can test it. I can count 3 of them right now that are for production, and also that can support efficient SPLE analysis, because it perform the analysis really fast, and you just need to model. You just need one model. You don't need to have several models, extending models, and so on. And you are using something that already exists, that is category theory. And then as a future work, we want to support more type of extensions to analysis, because every time some new case study arises, you need more things to add to those models. And also to integrate quality models. What we did was using quality attributes model, but quality models are also another field of pseudo standards where you have different subtypes of quality, quality subtrees, and so on. Also tested with larger SPLs. There is another field on SPL that it's easy to, it isn't easy to solve, that are the colossal models, colossal SPLs, when you have 10 to the power of 100 different products. So we don't know yet how the IDE and these transformations will work. We are working as well on an automatic transformation tool from variability models to a category, to this framework, categorical theory variability models. Because for those large models, doing manually as we did for this work is not also the best procedure. It can be done, but it takes time and knowledge. And that was all. I didn't check the time. Hope that I didn't get too much of it. And thank you so much.
Thank you very much for this elaborate talk. You had a little bit more time than the others used because they have saved some time. So, and you have had the chance to go more into detail, I guess. Yeah, again, I would like to open it up for questions and comments, maybe also by the other presenters. Again, one question. One thing that you have in the paper but not presented in your talk is sort of a comparison. I mean, you have made a nice presentation within the world of category theory, but in the paper you also have a big table. You don't want to show that now, but maybe just make a general argument why this approach is actually better for your purpose of variability analysis than the competition. I mean, you have, please don't show it because it's really not the point to look at the details. It's maybe you can just make a general answer.
Yeah, sure. Yeah, it's true. When we decided for the category theory, even if it was the most obvious reason, because of its unification background, I didn't know about category theory before. Actually, I get into it following databases works, new kind of categorical databases.
Right.
And then as I didn't know, and category theory is also difficult to understand at first if you are not from the algebraic field. I got many options. Some of them from the SPL community, other ones from the algebraic community. For example, the first solution that we could think of, me and Dillian, was regarding the relational algebra, like the ones for databases and so on. But what we found is that it's not the same. The SQL language that you use in databases, like select, while, and so on, is not the same as the formalized relational algebra. You don't have things like that we will need, like cross-tree constraints in the sense of arithmetics and so on. You don't have many groupings. You don't have the halving. You don't have the joiningly. I mean, the advanced joins. That's not formalized. And then if this doesn't work on databases because it doesn't scale, as databases are more like linear and identity relationships. So we needed to drop the relational algebra. We check also higher order logic, but on higher order logic, because we need to cover that as well with these, we have variability models using higher order logic. You don't have arithmetics, for example. Then the regular variability model was it comes from the 90s, I think. It's called the FEODA. FEODA is the first formal variability model that we have. It didn't work as well because it's a Boolean Boolean and Boolean logic type of model. We have also the arithmetics, but on the pure arithmetics, pure calculations like MATLAB, what they were using are pseudo Booleans for the Boolean. So they are using 1 and zeros to reflect true and false instead of using a true solver for Boolean. Something that COL IDE in this work is doing doing a combination of different reasoners. That's why it's smart enough to know which part must run on this reasoner and on that reasoner. That's why it's fast. I can think of, I cannot remember. There were a few. There was also propositional logic, I think. But propositional logic is like a subset of the higher order logic. There is as well the algebra of sets. But category theory, there is a category of sets as well. So if you go to the category theory, you go upper the category of sets.
Okay. We have actually one more question now by David Benavides. Could you unmute him?
So we have one question. Questions and answers. Hi, Danny. Nice talk. It may be
you should now be able to ask your question.
Okay.
But switch on your microphone, please.
Hello. Do you want me to?
I'm sorry. Can you hear me?
Yes.
I can read it. Hi, Danny. Nice talk. It made me think that what is the added value of using CT for representing configuration variability problems? Is an exercise of conceptualization. Your implementation was done implementing a sort of CT solver. Did you use it or off the shelf? Greetings from Sevilla.
Yeah, I have all there are a few questions. I can answer them one by one. The first one, hello, David. I know him from the University of Seville. Nice that
what is the added value of using CT for representing configuration variability problems? Yeah,
exactly. First of all, you don't, when you are using this category theory, let's say like a language, like for programming, when you are extending things, you don't need to create something new. Like I will extend this model. Actually, you are not extending the model. You are just programming. You are just modeling something that can be modeled, including like attributes. You are more familiar with attributes. You can do that. And also, you don't need then the problem that I extended this model, but the reasoner is not compatible with it because I need to extend the reasoner to be compatible with that new feature of the capabilities of that model. And it wasn't an exercise of conceptualization. It was a running exercise, a needed for solving. As I mentioned before, I was working with a hybrid solution. Your implementation it is, well, the implementation wasn't you mean the David, you mean the original, the one that I was using a hybrid model, or the new one? The original one was, yes, half it was a constraint programming solver plus a database, but this one it's a combination of not city solvers, theorem prover solvers. Some of them are from databases like the CAiSE algorithm. So the COL IDE is using a combination of them. It's similar like other reasoners as SMT, like C3 works, that depending if you are just using Boolean, it runs on a SAT solver, and if you are using bits are running on the SMT solver, and so on. So it's smart enough to do it. And yeah, off the shelf.
Thank you very much. And David actually has said that he has understood. I would now like to thank all of the speakers and also Anna for technical support for this session, and all the listeners. Well, I guess so for some of you it's late night, and for others it's like myself, it's just another item to continue the day. So I think it was a very interesting session altogether, and I would like to wish all of you a nice conference, and thanks for your contributions.
Thank you very much. please join the work session. That is a different link.